Hello and welcome to the Innovate-A-Thon Discussion,
where we cover everything going on in the world of innovation, creativity, workforce advancement, entrepreneurial thinking, and enabling the next generation to do good in the world. We're going to explore interesting topics with mentors, students, and innovators who are shaping the future in different industries. So today, we have Matt Shomper as a special guest on the Innovate-A-Thon podcast. So welcome, Matt. Thanks for coming. Very excited to talk with you about interesting topics in your background, maybe dive in a little bit too of just using biomimicry, talking about innovative applications for biomimicry. You have a little bit of background too in, being a part of new businesses. And so we'll probably talk through a little bit of that too as we go through your background. And then we'll go through a little bit of show and tell too. We'll bring in something to just talk through, something interesting, and then we'll kind of end and leave it at that. So I'll give my introduction first. So I'm Steven Semetzik. I am the director for the Innovate-A-Thon program. My background is in engineering, entrepreneurship. So excited to have Matt here today too, because we get to talk a little bit engineering, computational design, some of the things that I've also been interested in my career and been a part of. And then I joined the team for the Innovate-A-Thon at the very beginning of this last year, driving the program forward, enabling the next generation to take some of these new innovative things like computational design, new innovative ways to think about product solutions and put them into action. So that's a little bit of me. Natalie, do you want to go? And then we'll...
Yeah. Hi guys, I'm Natalie. I've worked with Innovate-A-Thon for about 3 years now. My background is in communication and public relations, and a lot of what I focus on is outreach to students and public relations.
Awesome. Matt, if you want to go for it and give us kind of your background, your story, and then we'll get into it. Yeah.
My name is Matt Shomper, as Steven said. My last name is much easier to say than Stevens. I think we've been friends for a few years, and I still can't reliably pronounce your last name.
Yeah, it's a bad Polish Americanized version that I even say so.
So yeah, my background primarily has been in the medical device space. It's where I started my career out of in implants, specifically for orthopedic devices, the spine. And over the years of career development, got into 3D printing and, kind of meandered my way because 3D printing could produce cool shapes. The software tools needed to catch up to it. So found myself becoming a power user by necessity of all the various emerging tools that allowed for you to really be able to explore 3D geometry. So now my primary role is essentially a consultant for companies that are looking to innovate with 3D printing and using those principles of design for additive manufacturing and computational design to help with product development. So anything from parts going into people's bodies to, parts going up in planes, things that you might wear. And over the last couple of years, I've had the privilege of working in a myriad of different industries.
And I wanted to start too, where did your obsession with biomimicry start? Where was the origin of that?
It's probably been about a decade ago, and I think I might have told this story before, but as you start having kids, you start becoming more interested in the children's shows, mostly by necessity, right? You just have to sit and watch what they want to watch. You don't get to watch your shows anymore. So of course, as wanting to be intentional parents, we didn't want to throw them in front of Coco Melon or I don't know, whatever was on at the time, some YouTube randomness. We wanted to be all right, you get to watch an educational show.
Slightly less mindless.
And a lot of these shows are, that are teaching about animals, typically will dive into a particular aspect of the animal. So, typically they don't go as deep as structural, microstructure, under a microscope. Oftentimes they'll say a cool fact about an animal. And I was always fascinated by the facts, right? Which seem innocuous to a child. An alligator has a bite force of whatever, 2 tons or whatever the number is. And kids are cool, I'll log that away in my brain and never use it again. But for me, my fascination was more about, like, as an engineer, what structures allow that to happen. And then, after the bite occurs, right, there's the teeth, right? What's special about an alligator's teeth that allow them to not break if they're biting onto something with that much force, right? Crunching through, bones. So that's, I would say, a decade-ish ago, when I started to be like, man, there's so much cool stuff out in nature. And, I don't know, guys, taught my kids shows. The mantis shrimp, my absolute favorite animal, who is up on the wall over here somewhere. My wife had a custom mantis shrimp art for me. I don't know exactly where it's at. And it just the structures that are in the mantis shrimp's appendages that allow it to, like, club through the armor of crabs and other crustaceans under the water is just fascinating. So, I think any pattern, structure, texture that you see out in nature somewhere is an opportunity for exploration, and my brain just latches onto those and wants to figure out why.
Yeah. Did I ever tell you that? So I knew about the mantis shrimp, but I actually did. It's funny. I learned about it more from a kid's show, Octonauts.
Oh yeah, Octonauts.
They have a whole episode on mantis shrimp, and that was like my first like, oh wow, yeah, they're pretty great, and they do battle in there, and
yeah,
mantis shrimp.
What I think is funny is, I had done the study on, like, a mantis shrimp structure. At this point, it's probably getting close to, like, 5 or 6 years ago, which basically was like, I want to computationally model this and put it in stuff. Well, that Octonauts episode was on because I think our third kid became obsessed with the show. That's when I first realized that there were two versions. There was the club guy that I was familiar with, but there's also a guy who's got a spear, and so his actuating method, rather than clubbing things and breaking their armor, is to literally just spear fish, spear their fish. And this is kind of a tangent, but apparently, I gotta watch my language. But apparently the mantis shrimp are like the jerks of the sea. So if you ever have them in an aquarium, they will needlessly murder other things in their environment, not even to eat them, just because they're like,
oh my gosh,
get out of my space.
They're just murderers.
Little assassins, right? Yeah.
And I'll do a plug for those of you who have children. There is a game called Mantis, which is super simple, fun to play. It's just a very simple card game, and my kids and I just love to play that. Our toddler is 3. He can even play the game, so it's got cool art.
Yeah,
teaches them about mantis shrimps.
Yeah, don't tell me these things, because I'll spend a half a day on a weekend. Cool. Yeah, and I think too, so background too, I started following you on LinkedIn before I met you, and I was just super fascinated too. I was trying to find the original book that I read for biomimicry, talking about applications for shark scales and shell structures and a whole bunch of other things. And then, I'm pretty sure one of the first posts I saw was your ram horn, and actually talking through that. And so I started getting deeper computational design, and being really curious just about taking those types of just natural discoveries of those structures, and then thinking about, you could actually apply that to a whole application. And so many ideas can kind of come just from these inspirations, and it's very cool to just think about, okay, just go take a walk, right? Go walk down, walk down through your nature path, look around, start identifying things that, why do they do this? Like, what is the origin of, how something behaves in nature? Why does it make this structure to, basically adapt or to sustain? And how can that be used for things that we think about and coming up with new ideas?
Right. Yeah. I mean, you're right. The way I always saw it was, you have hundreds or thousands or millions of examples, literally just around you, that exist in the world. And as engineers, we we want to design the best use application for whatever like we're designing for. And obviously we've got to consider a myriad of different factors, right? What's the envelope, materials, things like that. But when it comes to optimizing those, it's like we can definitely look at, you know, things that in nature have already been pre-optimized for their special built purpose. And I often say this, right? Regardless of whether you think things were, you know, intelligently created by a designer or whether they evolved over millions of years, it really doesn't matter. The fact is they're still purpose built. They've been purpose built, you know, either through millions of years or otherwise, to do a specific task. And the other thing that is interesting from an engineering standpoint that I always tell like younger engineers is it's one thing to look at a structure in nature and be like, well, this is what it's used for. So like the feet of a gecko are really interesting. Like they've got these fibrous appendages that are incredibly small, and they essentially keep branching down to, you know, I mean, at the nanometer level. And so when basically the surface area at the end of these fibers at the tip of their feet use a fundamental force of nature called van der Waals forces. So the reason they stick to something isn't because they're inherently sticky. It's because they're making use of a fundamental natural force that's similar to like the bonds between atoms. But you can't scale that up. If you scale that up, you lose what made it special at that particular size. So you can't always just like plug and play. Capillary action's another thing, right? You've seen things that can wick moisture. Well, scaling up something that's small that wicks moisture at a particular size doesn't work if you scale up to, let's say, like a wetsuit or something. So you have to also understand like what material am I making out of? It's probably not going to be biological in nature. And then what, you know, when I scale it, do I fundamentally break the nature of the mechanics of materials that made it? So yeah, it's not like I'll just steal this and use it for my own purpose. You know, you still got to do some
the legwork, right? To like, take it from more of a micro level to, more of a macro level application where it can actually be used. Yeah.
An example of something that I found that kind of helped me to understand biomimicry a lot more, because I was like, what is this? When I was researching it, I was like, goodness, it's like completely out of my wheelhouse. But I found that Velcro was inspired by like sticker burrs. Like a guy had them, like they got stuck to his dog, and he like developed the Velcro just from the sticker burr, like looking at that and like seeing how the little hooks go together and then come apart. So that was pretty interesting to me, seeing that.
Yeah. Those weird discoveries.
And the bullet train, which was inspired by the kingfisher beak, and I think it was in Japan. That was pretty interesting too.
I give a plug, but I actually was accepted to give a presentation at Rapid this year, which will actually be the first time I have attempted before. And I think 2 previous years I had to cancel my talk for extenuating circumstances, but I actually have 3 new kind of never before seen structures that I am computationally modeling that are inspired from nature. Because this will be the 3rd of a series that I've done, which is basically like, hey, here's this really cool thing in nature. Why does it do what it does? Let's reduce it into its basic structure, model it, and then print some things out and squish them, for lack of a better term. So one of the new things that I'm fascinated with is, I think I've posted a couple times on it before, is the diabolical ironclad beetle, which basically has the coolest name of any bug in existence. But it's like called the unsquishable bug. You could drive a car over it and it's no worse for the wear. So, but basically it's got this incredibly cool fibrous, like puzzle interlocking exoskeleton, which I think is fascinating for like body armor or like flexible, like, you know, really strong armor that also needs to have some semblance of movement to it for like armored vehicles or something. So
gotcha.
Yeah, I mean there's no absence of fun things that you can get inspired by, that's for sure.
Yeah, and I think too, I'll try not to go too far on this, because having fun with doing simple experiments too, of where you're doing pull tests, like compression tests, and then literally it's, you know, you're in this world too. It's like, oh man, I could make, you know, this many sample coupons and just, you know, start testing this, and then you get that feedback too, and that's exciting when you start taking that structure, scale it up, and then you
Right.
start getting that feedback loop going.
And maybe there you can touch on like the entrepreneurial nature of that, because I know that's a focus here, is like I don't want to say back in the day, but like there was a very like measured way I feel like engineers were supposed to act in their careers 20, 30 years ago. And this idea about like, a second job or exploration outside of your main career was virtually non-existent, right? You did your career, you got your pension, you worked your way up in the company and everything was great. Nowadays, it almost feels like if you're not working on something on the side, people are like, what are you doing with your life? That
Why aren't you tinkering in your garage? Like,
I just for fun, I browse Reddit, I've got like the various subreddits that I have interest in, 3D printing is a good one, but there's one called like overworking, and it's basically people who like brag about how many jobs they can hold at one time. And this idea of like the entrepreneurial spirit is just that, like what you're talking about. It's not just finding something you think is cool, or reading a fact, scrolling on and being like, that's neat. It's really being curious about what can I do with this. And now that we've got accessibility to home 3D printers, your ability to find something that looks cool, model it using CAD. That's a lot of CAD is either free or extraordinarily cheap for people to have nowadays. And then have a home 3D printer, which you can buy for under $200 sometimes, and then have something you can play with, really like piques your interest. And then like, it's like, you can do something with that. If you really have this, I want to do something, I want to change the world, you no longer have to like, well, shoot, how am I going to get this manufactured, or how would I even go about this? You can literally just in your garage for a few $100, like, design a product now and like figure out, obviously you've got to market and sell it, but the barrier for entry is a lot lower for entrepreneurs, I feel like, nowadays than what it used to be.
Yep. Yeah, and I think too, so we actually, in a previous, when we were talking about like tools that you use and some frameworks, and we talked a lot about, the Thomas Edison, mindset of going in and testing out unclaimed like 6,000 different configurations for a light bulb filament.
Yeah.
And like what the level that it took him to do that, where now, like you just said, you have a 3D printer. If you have a decent 3D printer, you could print out, I don't want to say 6,000, but a whole bunch, and do the testing like with very little, a lot less effort than it would take, even probably 10 years ago now. Like I keep comparing 10 years ago now, because that's when I first got like what I thought was like, oh, I'm getting a 3D printer, I'm going to pay this money. And I started doing that. And then, literally like 3 to 4 years later, it got better. And then it keeps getting progressively better. And then now you got these printers now where you could do, it's almost like an eighth of the time comparatively with some of the new printers. I would say an eighth is even conservative. Like some of these printers, these FDM printers can move at, absurd speeds. Like, I think that some of them might even have like a ludicrous speed mode, right? It's just like, I think some of the newer ones also have like vision systems, so that if they're moving so fast that everything's vibrating, they can track where the part is and compensate on the fly, which is mind-boggling to me as somebody I'm not a software guy. And, I'm a caveman engineer. I see stuff, I squish it, but I can see what happens. Get out of here with this electrical engineering stuff where you just gotta do a bunch of weird math and then hope it makes sense. That's I'm not smart enough for that. Yeah, I don't want to go into no plugs. Bamboo Labs printer, the one that like started using now, it's this total leap forward, like,
right.
And it has basically resonance compensation. Like it goes in and vibrates at frequencies to be able to print faster. So,
right.
And that's just nuts. And then it can, once it gets past the first layer, depending on what part you're making, it's just amazing to watch it. And it's that same feeling I had, over 10 years ago now, when I got, I started playing around in my garage, and that slower process of just sitting there, probably huffing in too many fumes, like just being fascinated by the process, and then it just leaps, and then it gets even better.
Right.
And then, yeah, now you have that access to be able to make all those starting points for your ideas, and even faster than before. So,
right.
Very cool. I wanted to ask you too, on startups in general. And I think too, I've been a part of things, we have kind of the entrepreneurial thinking type skill sets. They're basically just business tool sets that you can apply, in entrepreneurship to coming up with new ideas, moving towards more like an implementation, like how you can take an idea and implement it. You've been around to see the formation of companies and like trying to get, to that spot where they do that first, verification of something that might work, and they slowly progress to a spot where they're fully commercialized and they can make stuff. And I think, how much more time we want to spend talking here, but just kind of your background, maybe opinion. And I know you work with, startup companies now too, in those ways, just trying to get to a spot where they can scale up. So that's,
Yeah, so I put my business development hat on, which caveat, in most of the startups I've worked on, I am not the business development guy worrying about how things are going to get sold. I'm mostly interested in the technology behind the product. But the first thing that I always tell you is to evaluate product market fit. Like, you could have a really cool idea and maybe like, oh, this idea is going to change the world. But if there's not a market for it, it sounds bad, but it's like, as cool as your idea is not going to, like, it's not going to go anywhere if people don't want it, right? So that's the idea behind what's the demand. The other thing is, that there's obviously cost considerations. If it's a really cool product, but it's a new manufacturing method and it's 3 times the cost of other similar products, then again, you're going to, I think, struggle to gain a foothold. So the first thing I would say is like, making sure that your idea is feasible and that it's, it's something that the market is interested in. I'll mention the lattice robot thing that, some folks and I were working on, which I thought was a really cool idea, because these 3D printing structures can be so overly complicated, it can be hard to figure out why you would use one versus the other. So we created a website which allowed people to kind of browse the structures almost like as a material database. So engineers could say, like, it's kind of like, oh, I need to use aluminum or steel for this project. Well, it'd be like using lattice A versus B. The problem is, as cool as the site is, you also have to evaluate product market fit. Who's going to use it? So that, it turns out the number of interested interested people that would use it are a subsection of engineers, which are already a subsection of other disciplines. And then of those engineers, only a fraction of them are using 3D printed parts. And of that fraction that are using 3D printed parts, only a fraction of those are using complicated lattice structures in their parts. So it's like, okay, yeah, I've got this really cool tool, but we realize, well, it's a fraction of a fraction of a fraction of users. So, maybe the number might not be as big as we originally thought. So I think that, is like, it's what turns a passion project into a real product is, is there an intersection there between the two of what you really want to work on and like what the market actually wants? And I'm certainly not going to quote all the small business statistics, right? Most people probably are aware of them, right? That a lot of them fail for various reasons. So to me, it's just like, I've been really fortunate, and this is not career advice, but I've just been very fortunate to do what I love, for most of my career. Not that there haven't been times where I don't particularly like it. But I will harken back to Mike Rowe used to do that Dirty Jobs, and I don't know if people remember that or not.
Yeah,
so he was actually quoted as saying, and I'm obviously paraphrasing, but he basically, like, he had heard the phrase like, do what you love and you'll never work a day in your life, and he's like, that's BS. He was like, do what you're good at, so you can afford to do what you love in your free time. Which basically the sentiment was like, I want to do what I love. Well, I love underwater basket weaving. Well, darn it, I can't make any money doing it.
So
So
underwater basket weaving isn't going to pay your bills.
so I think, yeah, the entrepreneurial stuff is really cool, but it's also like a hard journey, and you don't just like happen into it because you have a good idea. Like it takes an incredible amount of work and making sure that like what you're working on. So, Stephen, I know that you've worked in various, started businesses and sold businesses, and you know that without a doubt, I'm sure that.
Yes, painfully in some cases. And it's those two, having that addressable market, which you already talked about. It's like this shrinking subsection that is actually going to be the ones that are the primary users, the ones that are your ongoing revenue, the ones that do basically make it work. And then that's the great part. It can start as passion, but then it's like this intersection between what is feasible and passion. It's like this Venn diagram that they have.
Yeah, I mean the world would be a much better place if everybody could only do what they love to do. But I don't think the world would function like it's supposed to.
Yeah.
Very cool. Well, I'm going to go to the next little segment, so we have at least enough time to talk it. Did you have something to show? We could do a little show and tell, just something to talk through so people can see things. And a lot of people that might be watching might not be familiar with additive manufacturing or 3D printing as much, or have the basis for what a lattice is. So,
all right. So,
yeah.
I'm only pulling this up because it can directly relate to something that's biomimetic. Actually, they've got two examples. One, which I hate showing because I don't like the structure. And I have railed against it before, so I've got a couple of pens. These were made by my friends at RMS Machining. They've got a great 3D printing group. They do 3D printed titanium. So these 3D prints are, there's nothing really functional about them, but just for fun. But what you see here is a cellular structure called Voronoi. I think the Voronoi algorithm has existed in 2D for decades. It's essentially just a way to sort of tessellate space. You'll notice here that like each of the cells is a polygon, but the cells are not regular. There's some disorder to them. So some of the cells may be a little larger, some may be smaller. Sometimes they're 5 sides, 6 sides, or 7 sides, but generally speaking, you've got a structure. You can look at this or take a screenshot of this and then look at like the pattern on a giraffe. Most people, when you say Voronoi, I just say, look at the spots on a giraffe. They naturally order themselves into a Voronoi pattern. I don't know why. I've never really researched like if that's something that happens probably when they're forming in the womb, but again, their pattern naturally divides into a Voronoi pattern. Versus this is more of a hexagonal structure. So these are just hexes, something that you would see in a hive, beehive. Now, in this case, they're just pens, so they're just made to look pretty. But in a engineering case, you have, like let's say I was wanting to use one structure or the other. Both you could reasonably say they're the same cell size, the same strut size, but there's actually quite a few different mechanical properties associated with each of them. And diving into those properties, we won't do here. But, again, the idea of like 3D printed cellular structures, why you would use one versus the other. Oh, I got a cat joining me.
Special guest.
They don't want to see you. Special guest. So yeah, can 3D printed structures just look cool and pretty? Sure, there's an aesthetic quality to them. But, a regular ordered structure like honeycomb is nice for predictable mechanical properties. Something that's a little bit more random, you may have less predictable properties, but they're really great for things like fatigue resistance, because when they start to crack, under a fatigue load, the crack doesn't propagate across all the cells in a ordered, like right in a straight line. It kind of has to weave through. So they're actually a lot better for impact resistance type stuff. So if you see like foams, a lot of times foams are just, they're randomly oriented for that very reason. So Yeah, I think this is just what I think is fun. This is another little fun piece. See here. So I actually posted a little bit about this. This is kind of a spiral sort of spring type structure. And from what I heard, incredibly hard to 3D print in metal. But so I'll be talking a little bit more about this in a video that I'll probably post to LinkedIn about this. And this was inspired by a nautilus shell. So if you want to just see like a perfect example of something was naturally created that is incredibly beautiful, look at a section view of a nautilus shell. I mean, it's like a perfect spiral. It's hard to explain how the spacing and everything, the radial fins and everything are just like perfectly ordered. The spiral is like the same every single time, which there's physical laws which dictate kind of how those form, which is another cool thing. But yeah, I just fascinated by it.
Yeah, very cool. That more like a pure golden ratio, like.
Yeah, exactly. What is that? 1.6 something.
Yeah.
The golden ratio, but the golden ratio defines those sort of spiral patterns, which exist in nature, which is pretty interesting.
Yes, I know. We could keep going. so this, yeah, fascinating stuff. Now, I think we're gonna end it here, but I thank you so much for coming on and just talking with us today. Like curiosity spikes, we might have to have you on again to talk about more. But we appreciate you coming on, giving your background, and being on the podcast today. And
thank you. I definitely learned a lot, especially not being from this background. So it's interesting to hear about all the different honeybee hives and things like that you wouldn't normally think apply to the real life, how you could transition it and change it. But very interesting.
Mm-hmm. Cool. Yeah, thanks for having me.
Yep. All right. Well, thank you everybody for joining the Innovate-A-Thon podcast. We'll see you next time.